After about 1 Google years, even the last black hole may evaporate, leaving the universe with no stars, no matter, and no time as we understand it. But the most shocking idea is this, that death may not be the end. It may be the moment the universe prepares for another Big Bang. Before we go further, take 1 second to like and subscribe, because this may be the strangest ending science has ever proposed. Get ready, we begin. Everything ends. You already know this. The candle on your dinner table burns down to nothing. The battery in your phone drains until the screen goes dark. Every human being who has ever lived has died. These aren't tragedies. They are just the rules. And for over 150 years, physics has been telling us, with increasing precision and increasing confidence, that the universe plays by the exact same rules. It was born, it is aging, and one day in a time frame so incomprehensibly distant that the word day becomes almost offensive, it will die. This isn't speculation. This isn't a fringe theory scribbled on a napkin at a conference. This is the conclusion of the second law of thermodynamics, one of the most tested, most robust, most mercilessly confirmed laws in all of science. The law states this in any closed system. Entropy, the measure of disorder, of randomness, of how spread out energy becomes, always increases. Always. No exceptions. No loopholes. You cannot unscramble an egg. You cannot unburn wood. You cannot take the warmth that has already leaked out of your coffee and push it back in without spending more energy than you recover. The universe is a one-way street, and the sign at the end reads maximum disorder. Every star you have ever looked at in the night sky is a battle against that law. A temporary, beautiful, losing battle. Now, let's talk about how long this dying actually takes, because the numbers are where the real vertigo begins. The stars go first, not anytime soon. Obviously, our sun has about 5 billion years left on its main sequence, but zoom out far enough, wait long enough, and all stellar fuel runs out. In roughly 100 trillion years, that's 10 to the power of 14 years. Written as the number 1 followed by 14 zeros, the last stars in the universe will exhaust their hydrogen, collapse or fade, and go cold. The night sky, which humanity has navigated and worshipped and written poetry about for our entire existence, will simply go black. No new stars will ignite. The era of light, which we currently live inside without even thinking about it, will be over. But the universe is still far from finished dying. After the stars are gone, what remains? Stellar remnants, white dwarfs, neutron stars, cold dead cores drifting through absolute darkness, and black holes, enormous, ancient, patient black holes. If protons, the particles that make up the nuclei of every atom in your body, in this planet, in everything, if protons are not perfectly stable, if they eventually decay as certain theoretical models predict, then even those cold remnants will eventually dissolve. The estimated timescale for proton decay runs to approximately 10 to the power of 40 years, 10,000 trillion years. By that point, ordinary matter as we understand it may simply cease to exist. And the black holes? They outlast everything through a process called Hawking radiation, a slow, quantum mechanical leak that Stephen Hawking predicted in 1974. Even the largest black holes will gradually evaporate. The most massive black holes in the universe, the supermassive giants at the centers of galaxies, will take approximately 1 Google years to fully evaporate. 1 Google is 10 to the power of 100. That is the number 1 followed by 100 zeros. Pause on that for a moment. The total number of atoms in the entire observable universe, every star, every planet, every cloud of gas, every grain of dust across 93 billion light years of space, is estimated at around 10 to the power of 80. 10 to the 80th power. 1 googol is 10 to the 100th power. That means 1 googol is 10 billion times larger than the total number of atoms in everything we can observe. The universe will spend more time slowly evaporating its last black hole than the total count of its own atoms could ever represent, even if each atom stood for an entire year. That number doesn't just break your intuition, it erases it, and what comes after the last black hole is gone. Nothing happens. That's the point. The universe reaches a state that physicists call heat death, and the name is almost poetically misleading. Because there is no heat, there is no event, there is no drama. The universe becomes an infinite expanse of space, hovering just above absolute zero, which is negative 273.15 degrees Celsius, the coldest temperature physically possible. Drifting through this frozen void will be photons, particles of light, and a thin scattering of other massless radiation, all moving freely, never interacting, never colliding in any meaningful way, never producing anything new. Think of it this way. You make a cup of coffee in the morning. Hot, steaming, fragrant. You set it down and forget about it. An hour later, it's cold. The heat didn't disappear. It spread. It diffused into the air of the room, distributed itself so evenly across so many molecules that no useful temperature difference remains. You can no longer use that heat to do anything. The energy is still technically there, but it's been smeared into uselessness. The universe is doing exactly this, just at a scale with no analogy that can hold the weight of it. Every star is a hot cup of coffee surrounded by the cold of space, and the universe's entire history is the story of that heat spreading, that temperature difference flattening, that gradient collapsing toward zero. When heat death arrives, the gradient is gone. No chemistry can happen. No light can be created. No clock can tick. No thought can form. The universe will not explode or collapse or scream. It will simply stop having events. Most scientists look at this picture and accept it as the final chapter. A complete, if deeply melancholy, story. The universe had a beginning. It will have an end, and the end is silence. If that's true, if everything you love, every civilization that has ever risen, every idea that has ever mattered, every question that has ever been asked is destined to dissolve into an infinite cold dark, then why, in the name of all of it, did any of this get started in the first place? The universe is spending 1 googol years dying, and here we are, anxious about tomorrow's deadline. At least we have our priorities straight. But one man looked at this perfectly constructed picture of cosmic death, and instead of seeing an ending, he saw a question that no one in the history of physics had ever actually answered. Black holes aren't black. That sentence alone should stop you. Everything you've been told, every documentary, every textbook diagram, every dramatic visualization of a void so dense that nothing escapes, carries the implicit assumption that black holes are the ultimate dead ends of the universe, objects of pure, final, irreversible consumption. You fall in, you don't come back, end of story. Stephen Hawking looked at that assumption in 1974 and said not quite. What Hawking discovered theoretically, through a marriage of quantum mechanics and general relativity that still makes physicists uncomfortable, is that black holes radiate. Slowly, imperceptibly, slowly by any human standard, but they radiate, they lose mass, they shrink, and given enough time, they evaporate completely, leaving behind nothing but a faint pulse of thermal radiation spreading outward into the void. The mechanism responsible for this is one of the strangest things quantum physics has ever produced. At the edge of a black hole, the boundary called the event horizon, the point of no return's empty space is not actually empty. Quantum mechanics forbids true emptiness. Instead, the vacuum of space seethes constantly with what physicists call virtual particle pairs, a particle and its antiparticle flickering into existence together. borrowing energy from the vacuum for a fraction of an instant, then annihilating each other and paying the energy back. Under normal circumstances, they appear and vanish so fast that nothing detectable ever happens. The vacuum stays, for all practical purposes, invisible. But right at the event horizon, something different occurs. Imagine two close friends who go absolutely everywhere together. They're inseparable, born together, destined to cancel each other out within moments of appearing. Now imagine they're walking past an elevator and the doors slam open and one of them gets yanked inside before either one can react. The doors close. The friend outside is suddenly, inexplicably free. And because the energy that should have been returned to the vacuum never gets repaid, the black hole itself foots the bill. The surviving particle escapes carrying real energy, drawn directly from the black hole's mass. That's Hawking radiation, not a metaphor. That's genuinely, structurally, what the mathematics describes. One particle falls in, one particle escapes. The black hole, across unimaginable stretches of time, slowly loses mass with every such event, drip by drip by drip, across timescales that make the current age of the universe look like a rounding error. How slow? A black hole with the same mass as our sun would take approximately 2 times 10 to the power of 67 years to fully evaporate through Hawking radiation. Written out, that's a 2 followed by 67 zeros. The current age of the universe is roughly 13.8 billion years, 10 to the power of 10. Roughly, the evaporation time for a solar mass black hole is therefore not just longer, it's longer by a factor that language can't really carry. And a supermassive black hole, the kind that anchors entire galaxies at their centers, millions or billions of times the mass of the sun takes up to 1 Google years, 10 to the power of 100, to evaporate completely. We covered that number in part 1. We know what it means. It's bigger than the count of atoms in the observable universe. It is, by any reasonable measure, the closest thing physics has to forever, while still technically being finite. But it does end. That's the point. When the last supermassive black hole finally evaporates, when that final drip of Hawking radiation disperses into the dark, what remains is a universe containing only photons and other massless particles. No atoms, no molecules, no dust, no remnants of stars or planets or anything that was ever solid. Mass, as a property of matter, is simply gone. The universe at that stage is pure radiation light and its relatives moving freely through infinite space, never colliding with anything meaningful, never forming anything new, never measuring anything. This is the state that most physicists accept as the final frame. The screen goes dark. The story is over. Roger Penrose looked at that final frame and felt something strange. Not grief, not resignation, something more like recognition. Because the state of the universe at its very end, cold, empty, dominated entirely by massless radiation, with no mass-bearing particles left to define a scale or tick a clock, bore a haunting mathematical resemblance to a state he had seen before, not in the future, in the past, specifically in the equations describing the universe in its very first moments, fractions of a second after the Big Bang, when temperatures were so extreme that the mass of particles became negligible compared to their kinetic energy. When, in a precise mathematical sense, the universe was also dominated by radiation, also operating in a regime where mass barely mattered, also exhibiting a certain geometric property that physicists call conformal invariance. The end looked like the beginning, not poetically, mathematically. Now you might be thinking exactly what most physicists thought when Penrose first proposed this. The man is brilliant, undeniably. He shared the Nobel Prize in Physics in 2020 for his work proving that black holes are a direct consequence of general relativity. But he's also in his 90s, And perhaps he's seeing patterns where none exist. Pattern recognition is, after all, one of the most deeply human cognitive biases. We see faces in clouds. We find constellations in random stars. Maybe Penrose is doing the same thing, just with more elegant mathematics. That thought is reasonable. Hold on to it, but ask yourself this: what if the mathematics actually holds up? What if the resemblance between the universe's first moments and its last moments isn't a coincidence or a projection? What if it's a structural feature of how space-time geometry works? What if the equations are not lying? That's not a rhetorical appeal to authority. That's the actual question on the table. And it has an answer, one that requires us to go somewhere most physicists have deliberately avoided going, to confront a problem buried at the very foundation of cosmology. A problem so uncomfortable that the standard response has been to explain everything around it while quietly pretending it isn't there. To understand why Penrose believes what he believes, we need to travel back before the Big Bang itself and face a problem that no physicist has ever truly been willing to look straight at. The Big Bang happened. That's not up for debate. The evidence is overwhelming, converging from multiple independent directions simultaneously. The cosmic microwave background, that faint glow of thermal radiation permeating every direction of the sky, first detected by Arno Penzias and Robert Wilson in 1965, is the literal afterglow of the early universe. Light from when the cosmos was only 380,000 years old. Still visible today after traveling 13.8 billion years to reach our instruments. The expansion of galaxies, measured first by Edwin Hubble in 1929, tells us that if you run the cosmic film backward, everything converges to a single point. The ratio of hydrogen to helium in the universe, roughly 3/4, hydrogen to 1/4 helium by mass, matches with extraordinary precision the predictions of Big Bang nucleosynthesis, the nuclear reactions that occurred in the first 3 minutes of existence. These 3 lines of evidence alone, entirely independent of each other, all point to the same origin story. So yes, the Big Bang happened. The problem isn't whether it happened. The problem is what kind of explosion it was. Most people, when they hear Big Bang, picture something like an explosion in the conventional sense: chaotic, violent, random, the kind of event where order shatters into disorder, where structure collapses into fragments, where entropy spikes. A bomb going off in a city doesn't leave behind a neatly organized grid of streets. It leaves rubble. That's what explosions do. That's what the second law of thermodynamics says they should do. Now imagine you drop a box of 10,000 Lego bricks from the top of a building. They hit the pavement and scatter in every direction. That's an explosion of sorts, chaotic, entropic, exactly what physics expects. Nobody looks at the resulting pile and finds a perfectly assembled spaceship. The Big Bang assembled a spaceship. Not literally, but that's the closest analogy for what actually happened. The universe did not emerge from its initial state in chaos. It emerged in a condition of breathtaking, almost incomprehensible order, a state of extraordinarily low entropy that made every subsequent event in cosmic history possible. Stars, galaxies, planets, oceans, cells, brains, symphonies, all of it runs on the stored potential of that initial order. Like civilization running on oil that took millions of years to form. The question physics has been quietly avoiding, not loudly, not openly, but avoiding nonetheless, is why. Roger Penrose sat down and actually calculated the probability. What are the odds that the universe randomly began in a state of entropy low enough to produce the cosmos we observe? The answer he arrived at is a fraction with 1 on top and 10 to the power of 10 to the power of 123 on the bottom. That's not 10 to the 123rd. That's 10 raised to the power of a number that is itself 10 to the 123rd. To write that denominator out in full, if each digit were the size of a proton, the tiny particle at the core of every atom, you would need a sheet of paper vastly larger than the entire observable universe just to fit the exponent. Not the number itself, the exponent. The universe we can see, all 93 billion light-years of it, is not remotely large enough to contain even the label for how improbable our starting conditions were. This is not a small probability. This is not even an astronomically small probability in the usual sense. This is a number so far beyond, effectively impossible, that the entire concept of probability starts to feel like the wrong tool for the job. Statisticians don't really have language for it. The universe, by all rights, should not have started this way. If the universe cannot have randomly begun in this state, then what, or who, set it up this way? Physicists call this the fine-tuning problem, which is, admittedly, a very restrained name for something that should probably be called the "why does anything exist at all, and how is this not the central crisis of all human knowledge" problem. Outside of physics departments, people who stumble across this fact at 2 in the morning call it the reason they can't sleep. The most widely accepted partial solution is cosmic inflation, proposed by physicist Alan Guth in 1980. Inflation theory says that in the first tiny fraction of a second after the Big Bang, we're talking something like 10 to the negative 36 seconds, the universe underwent a period of exponential expansion, blowing up by a factor of at least 10 to the 26 in an almost instantaneous burst. This elegantly explains 3 otherwise puzzling features: why the universe appears geometrically flat, why the cosmic microwave background is so uniform in temperature across regions that should never have been in contact with each other, and why we don't observe magnetic monopoles that early universe physics predicts should be everywhere. Inflation works beautifully for all of that. But here's what it doesn't explain. Inflation had to start somewhere. It had to begin in a region of space that was already in the right condition, already low enough in entropy to trigger and sustain that expansion. Asking why the universe has low entropy and answering, because inflation, is logically equivalent to explaining why your apartment is spotless by saying, "I hired a cleaner." Useful information, certainly, but it doesn't explain where the cleaner came from, why the cleaner exists, or who paid for them before the concept of money existed. Inflation pushes the entropy problem backward in time. It doesn't dissolve it. The universe needed a preposterously ordered starting point. Inflation cannot account for why that starting point existed. Every other theory in the cosmologist's toolkit, string landscape, Hartley-Hawking no-boundary proposal, eternal inflation, either relocates the problem, multiplies it across infinitely many unobservable universes, or quietly requires that you stop asking follow-up questions. None of them answer the actual question. Penrose looked at this situation, this impasse that has sat at the foundation of cosmology for decades, like a crack no one mentions, and refused to look away from it. His response was not to reach backward in time for an explanation before the Big Bang. It was to look forward, all the way forward, past the death of stars, past the evaporation of black holes, past the last photon in an empty universe. His answer, he said, was not hiding before the Big Bang. It was hiding at the end. But to follow that answer, we first need to understand what entropy actually is, not the simplified version, but the real one. The version that reveals why the universe's low entropy beginning was not just improbable, but structurally, gravitationally, cosmically specific. Entropy gets a bad reputation as a synonym for mess, disorder, chaos. The reason your desk looks the way it does. That's not wrong. Exactly. But it's incomplete in a way that matters enormously for what comes next. The precise definition, the one Ludwig Boltzmann worked out in the 1870s and essentially died defending, is this entropy is the number of different microscopic arrangements a system can have while still looking the same from the outside, not how messy something looks. How many equivalent ways it could be configured without you being able to tell the difference. Consider a bedroom. A tidy one-bed made, clothes folded, books arranged by height on the shelf. How many ways can you arrange the contents of that room and still have it look that tidy? Very few. Maybe a handful of configurations qualify as neat by any reasonable standard. Low entropy means few available arrangements. The system's constrained, specific, almost unique in its configuration. Now the same room. Clothes on the floor, books stacked randomly, half a pizza on the desk. How many ways can you arrange the contents and still have the room qualify as messy? Millions, billions. The exact position of each sock, the precise angle of each book, none of it matters to the classification of disaster zone. High entropy means an enormous number of indistinguishable microstates. The system is loose, unconstrained, could be any one of vast numbers of configurations. Entropy always increases because there are simply more ways to be disordered than to be ordered. When a system changes randomly, probability overwhelmingly favors moving toward one of the many high-entropy states rather than one of the few low-entropy ones. The universe doesn't want disorder, it just wanders, and disorder is statistically almost everywhere. This much is standard. Now apply it to the early universe, and something deeply strange emerges. The universe immediately after the Big Bang was extraordinarily hot. Temperatures exceeding 10 to the 32 Kelvin in the earliest moments, cooling rapidly, but still at staggering energies for the first several 100,000 years. Dense beyond imagination, matter and radiation crammed into a space incomparably smaller than anything we can picture. By the logic of a bedroom analogy, this should be high entropy. Hot, dense, chaotic sounds like maximum disorder. But it wasn't. And the reason is gravity. Gravity changes everything about how we count entropy in a universe-sized system. When matter is uniformly spread out, distributed evenly across space with no clumps, no concentrations, no structure, it looks smooth, featureless, almost boring. Your intuition says this is a low-energy, organized state. But gravitationally, uniformly distributed matter is sitting on an enormous reservoir of unrealized potential. Gravity wants to pull that matter together. It wants to form clumps, then clouds, then stars, then galaxies, then galaxy clusters. Every step of that gravitational collapse releases energy, increases total entropy, and generates structure. Think of it this way. A uniform spread of matter under gravity is like an uncarved block of clay. It appears simple, even plain, but it holds within itself every possible sculpture, every galaxy, every solar system, every planet capable of hosting life. The options are all still available. The potential is intact. That's precisely what low entropy means in a gravitational context. Maximum unrealized possibility. Maximum potential for future structure. The early universe was that uncarved block of clay, smooth, uniform, and therefore paradoxically, against all initial intuition at its lowest gravitational entropy. The highest possible degree of order that a matter-filled gravitational system can possess. And then, over 13.8 billion years, gravity did what gravity does. It pulled, matter clumped. The first clouds collapsed into the first stars, burning their nuclear fuel across millions or billions of years. Stars exploded as supernovae and seeded space with heavy elements. Heavier elements assembled into planets. On at least one planet, chemistry crossed some threshold into biology. Biology crossed a threshold into cognition. Cognition looked up at the sky and started building telescopes. Every step of that sequence, every star, every explosion, every molecule. Every thought was the universe caching in a portion of that original gravitational, low entropy reserve. Every event in cosmic history is entropy increasing. Every beautiful thing that has ever existed is entropy increasing. The Milky Way is entropy increasing. You are entropy increasing. We are not fighting entropy. We are made of it, powered by it. Expressions of a 13.8 billion year drawdown of the account that was opened on the first day. And that account is not empty, yet, not even close. According to cosmological estimates, the universe's entropy has increased substantially since the Big Bang, but we remain enormously far from thermal equilibrium. The process still has hundreds of trillions of years to run. We are not near the end. We are in the full sweep of cosmic time, still closer to the beginning than anything else. Somewhere in the early chapters of a story whose final pages won't be written for another 1 Google years, which makes the original question sharper, not softer. If entropy only ever increases, if it is the most ironclad one-way law in all of physics, never reversed, never reset, then how does a new universe begin with entropy low enough to do all of this again? Where does a fresh block of uncarved clay come from? You're probably thinking, it can't. If entropy only goes up, then a new cycle is physically impossible. The account can only drain. It can never be refilled. That objection is exactly right, and it's exactly the wall that every cyclic cosmology has crashed into. Except Penrose doesn't refill the account. He does something stranger and more elegant. He dissolves the accounting system itself. Before we get to that answer, we need to dismantle one of the most deeply held intuitions a human being possesses, the assumption that time is something real, measurable, and universal, because it isn't. And in the universe's final state, it won't exist at all. Time is the most obvious thing in the world. The clock on your wall, the alarm that pulls you out of sleep, the gray hair that wasn't there 5 years ago, the sun rising, crossing the sky, disappearing below the horizon in an arc so reliable that entire civilizations were built around predicting it. We don't think about time the way we think about gravity or electricity as forces to be studied and understood. We think about it the way fish think about water. It's just there. It's just what everything happens inside of. That assumption held up reasonably well for most of human history. Then Albert Einstein published his special theory of relativity in 1905, and the assumption turned out to be completely wrong. Time is not a constant. It does not flow at the same rate everywhere. It stretches and compresses depending on two things: how fast you're moving and how strong the gravitational field around you is. The faster you move, the slower your time passes relative to someone standing still. The deeper you sit in a gravitational well, closer to a massive object like a planet, the slower your clocks tick compared to someone farther away. This is not a theoretical quirk. It's not a rounding error. It's a measurable, engineering-relevant, daily reality. The GPS satellites orbiting Earth right now are a perfect example. They circle the planet at roughly 8,800 miles per hour, and they sit about 12,500 miles above the surface, in weaker gravity than we experience on the ground. Two effects act on their onboard atomic clocks simultaneously. Their velocity makes the clocks tick slightly slower relative to Earth, but the weaker gravity at altitude makes the clocks tick slightly faster. The net result is that GPS satellite clocks run fast by approximately 38 microseconds per day compared to clocks on the ground. 38 microseconds. That sounds trivial. It isn't. GPS works by measuring the precise timing of signals traveling at the speed of light between satellites and receivers. At the speed of light, 38 microseconds of timing error accumulates into a positional error of roughly 6 miles per day. Left uncorrected, every GPS device on the planet would drift by 6 miles every single day. Your navigation app would send you into a lake within a week. Engineers correct for this effect constantly, automatically, using Einstein's equations. Relativity is not an academic abstraction. It is load-bearing infrastructure. But that's just clocks running slightly fast or slightly slow. What Einstein's equations say about a particle moving at the actual speed of light is something far more radical. For a photon, a particle of light, moving at precisely 186,000 miles per second, the relativistic time dilation doesn't just slow down. It goes to zero, completely. A photon does not experience the passage of time. Not a little, not approximately, exactly zero. Think about what that means for sunlight. A photon is created through nuclear fusion deep inside the sun's core. It then embarks on a journey bouncing, being absorbed, being re-emitted, working its way through the dense solar interior for tens of thousands of years before finally escaping from the surface, at which point it crosses the 93 million miles between the sun and Earth in 8 minutes and 20 seconds by our clocks. From the moment it leaves the sun's surface to the moment it strikes your skin or your retina, 8 minutes and 20 seconds pass in our frame of reference. From the photon's frame of reference, 0 seconds, not 8 minutes. 0. The moment of emission and the moment of absorption are, for the photon itself, the same moment. There is no journey. There is no travel time. There is no between. You blink, and you are already at the destination, except even the blink doesn't happen, because a blink requires time, and time isn't available. So what actually is time? If a photon, a perfectly real, physically existing particle, one of the most fundamental constituents of the universe, genuinely experiences zero duration from birth to death, then time cannot be a universal background that everything exists within. It's something that emerges from the interaction of massive objects with each other and with space-time. It's something that requires mass to function. Without mass, without the ticking of particles that have inertia, that can be slowed, that carry internal clocks in the form of quantum oscillations. There is no time. Which leads to a question that seems almost too large to ask directly. If the universe's final state contains only photons and massless radiation, if every particle with mass has either decayed or fallen into a black hole and evaporated, then who, or what, is measuring time? What clock is left to tick? The answer is none. In a universe populated exclusively by photons, the concept of time becomes physically undefined. Not slow, not frozen, undefined. There is no mechanism left to distinguish before from after, no process that can mark the passage of duration, no reference frame from which the word now has meaning. Photons are, in the most literal physical sense, immortal. They do not age because aging requires time, and they have none. They do not experience boredom, no duration in which to be bored. They are never late, because lateness implies a schedule, and a schedule implies time. In some strange and genuine sense, the photon that left the surface of the sun 8 minutes and 20 seconds ago and the photon that will drift through an empty universe 1 Google years from now are, from their own perspective, the same immediate, timeless, complete. There's something almost enviable about that. Most of us can't get through a Tuesday without checking the clock at least 20 times. But the deeper implication isn't funny at all. If time ceases to be a physically meaningful concept in the universe's final state, and it does, then the universe at its end is not just cold and empty. It is temporally unmoored. It exists, in some sense, outside of time itself, which raises a possibility so strange that most physicists have simply refused to follow it to its logical conclusion. If there is no time in the final state, then final might not mean what we think it means. But photons don't just erase time. They erase the concept of size itself. And that opens the door to one of the strangest ideas in all of modern physics. Take two photographs of the same mountain range, one shot from 5 miles away, one from 50 miles. Different scales entirely. The nearby photo shows individual rock formations, snowfields, tree-line details. The distant photo shows the whole range as a single silhouette against the sky. Now crop them both, so each image fills the same frame. Are the angles the same? The proportions of peak to valley, the slope ratios, the geometric relationships between ridgelines? Yes, exactly the same. The mountain doesn't change shape when you step back. What changes is the ruler you're using to look at it. This is the intuition behind what physicists call conformal invariance. A system is conformally invariant if its physical laws stay identical when you rescale space and time, when you zoom in or zoom out by any factor you like. The angles, the ratios, the causal relationships between events all survive the rescaling. The absolute distances and durations do not matter. Only the geometry of relationships remains. In everyday life, this is a curiosity. In the context of the universe's final state, it becomes something else entirely. For a system to be perfectly conformally invariant, there is one strict requirement: all particles in that system must have zero mass. This is not arbitrary. Mass is what creates an absolute scale. A kilogram is a kilogram is a kilogram. It's a fixed unit, a reference point, a ruler built into the fabric of reality. When you have massive particles, you can always ask, how big is this really, and get a meaningful answer, because mass provides the measuring stick. Take away mass, and the question, how large is this, loses its referent. Large compared to what there is nothing left to compare against. This is the condition of the universe at heat death. Every massive particle gone, black holes evaporated. Only photons and massless radiation remain. No rulers, no clocks, no intrinsic scale. The universe at its end is, in the precise technical language of physics, conformally invariant. Now, go to the other extreme. The first fraction of the first second after the Big Bang. Temperatures above 10 to the 32. Kelvin so hot that the energy of every particle dwarfs its rest mass to the point of irrelevance. In that environment, the Higgs field, the quantum field responsible for giving particles their mass, had not yet switched on in a stable way for all species of particles. Many particles were effectively massless in practice because their thermal energy was so vastly greater than their mass energy that the mass term in the equations contributed almost nothing to their behavior. The universe in its first moments was, mathematically, operating in a near conformally invariant regime. Penrose saw this and felt the floor shift. The universe at its oldest cold, empty, massless, conformally invariant, and the universe at its youngest hot, dense, effectively massless, near conformally invariant, are, in the language of geometry, indistinguishable, not similar, not analogous, indistinguishable. Strip away the absolute scale, remove the rulers and the clocks, look only at the causal geometry, the structure of which events influence which other events, the angles of light cones. The conformal structure of spacetime and the two states map onto each other. A universe that has been expanding for 1 Google years, grown to a size incomprehensibly larger than what we can observe today, containing nothing but drifting photons and a point-like singularity exploding outward at the start of a new cosmic epoch. Same geometry, same conformal structure, different scale. But scale has no physical meaning in a conformally invariant system. Let that fully land. The way a universe looks just before it ends, and the way a universe looks just as it begins. These are not merely similar. They are, in a mathematically rigorous sense, the same physical state. The end of one universe and the beginning of another are separated by nothing more than a change of scale. And if scale doesn't exist, if there is no ruler left to measure it with, then that separation is not a separation at all. Think of it this way. You're looking at two circles drawn on a page. One has a radius of 1 inch. The other has a radius of 1 mile. In normal geometry, these are obviously different. But in conformal geometry, where you're only allowed to ask about angles and ratios, never about absolute distances, these two circles are identical. There is no geometric measurement you can perform within the rules of conformal geometry that distinguishes them. The dying universe and the newborn universe are those two circles. The scale is different. The scale is the only difference, and the scale has vanished. What Penrose realized is that this isn't a metaphor or an analogy. The mathematics of general relativity permits, in fact, under certain conditions, requires that the conformal boundary at the end of one universe and the conformal boundary at the beginning of the next can be identified with each other, sewn together, not metaphysically, geometrically, in the same framework that describes black holes and gravitational waves and the bending of light around galaxies in that same framework. These two boundaries are compatible surfaces that fit against each other without discontinuity. The ending of a universe is not a wall, it's a seam. If a dying universe that spans trillions of light years and a newborn Big Bang singularity are geometrically the same thing, then the line between ending and beginning has not just blurred, it has ceased to exist as a physical boundary. This is the moment Penrose makes the leap he calls conformal cyclic cosmology, and it overturns everything we thought we knew about beginnings and endings. The story we've been told about the universe has a clean, linear shape. 13.8 billion years ago, the Big Bang, a beginning, then expansion, cooling, the formation of hydrogen and helium, the ignition of the first stars, the assembly of galaxies, the slow emergence of planets and chemistry and life. Then, in the inconceivably distant future, more than one Google years from now, heat death, the ending, a straight line from birth to silence, from explosion to exhaustion, beginning, middle, end. This is the standard cosmological timeline, and it is supported by overwhelming evidence. No serious physicist disputes the broad strokes of it. The universe had an origin. It has been evolving. It will eventually reach a state of maximum entropy from which no further change is possible. What Roger Penrose disputes is not the evidence. He disputes the interpretation of what that final state actually is. In 2010, Penrose formally published the framework he called Conformal Cyclic Cosmology, CCC. The central claim is precise and mathematical, not poetic. The future conformal boundary of our universe, the geometric surface that represents the state of maximum expansion and heat death, can be identified, matched, joined, stitched together with the past conformal boundary of the next universe, the geometric surface that represents the Big Bang of the following cosmic epoch. To be clear about what this is and isn't, CCC is not a claim that the universe bounces. It is not the old idea of a big crunch, where the universe stops expanding, collapses back on itself, and re-explodes. That model has been effectively ruled out. We know from supernova observations confirmed in 1998 that the universe's expansion is not decelerating, it's accelerating. The universe will not collapse. It will expand forever. CCC accepts that completely. The universe expands. Forever. It reaches heat death. And then, not by reversing, not by bouncing, but by a geometric transition that requires no reversal. At all, it becomes the initial state of the next universe. The analogy that comes closest is this. Take an infinitely long sheet of paper. Draw a horizontal line across it from left to right. The left end and the right end never meet. The line extends to infinity in both directions. But now roll the paper into a cylinder. The left edge and the right edge which were infinitely far apart on the flat sheet, are now adjacent. They don't overlap, they touch. The geometry of the cylinder makes them neighbors without requiring either end to travel to reach the other. C doesn't physically curl the universe into a cylinder. It does something subtler. It recognizes that in the mathematical language of conformal geometry, the geometry of angles and ratios, stripped of all absolute scale, the distant future boundary and the immediate post-Big Bang boundary are already the same type of surface. They are already geometrically compatible. They already fit, like two puzzle pieces whose edges were cut by the same blade in different factories, in different eons, and yet slot together without friction. No physical mechanism needs to transport the universe from one state to the other. The transition is a geometric identification. The end of one epoch and the beginning of the next are the same geometric surface, described from two different sides. Now, return to the entropy problem, because this is where CCC does something no other cosmological model has managed. Heat death represents the highest possible entropy state of a universe. Maximum disorder. Everything spread out. Everything equilibrated. Nothing left to differentiate. The second law says entropy never decreases. So how can a new universe begin in a low entropy state? This has been the wall that every cyclic cosmology has crashed into. You cannot reset the entropy counter. The law forbids it. Penrose's answer in the final, conformally invariant state. The concept of entropy itself becomes undefined. Entropy counts the number of available microstates in a system. But to count microstates, you need a scale. You need to be able to distinguish between configurations, to say this arrangement is different from that one. When all massive particles are gone, when there are no clocks and no rulers, when the only inhabitants of the universe are massless photons for whom size and duration have no intrinsic meaning, the machinery required to define entropy simply doesn't exist anymore. You cannot ask, how many microstates does this system have? Because the question requires a measuring apparatus that the system no longer contains. The high entropy final state doesn't get reset. It gets dissolved. The entropy counter doesn't go back to zero. It becomes inapplicable. And on the other side of the conformal boundary, the new universe begins from what is, in the only terms that remain physically meaningful, a clean slate, a blank sheet, a state of extraordinarily low conformal entropy, not because anything was erased, but because the concept of high entropy evaporated along with the last massive particle. This is the solution to the fine-tuning problem that we laid out in Part 3. The improbably low entropy of the Big Bang doesn't require a supernatural setup or an inexplicable initial condition. It emerges naturally from the structure of the conformal transition. Every new universe inherits a low entropy starting point, not because someone arranged it, but because the conformal geometry of the transition guarantees it. Penrose calculated that this conformal matching produces a new universe that is smooth, flat, and free of singularities, precisely the characteristics we observe in our own cosmos, the flatness of space on large scales, confirmed by cosmic microwave background measurements to within a fraction of a percent. The large-scale homogeneity of matter distribution, uniform to roughly 1 part in 100,000. These are not accidents in the CCC framework. They are geometric consequences of the conformal transition from the previous aeon. If this is right, if the death of a universe is not a termination, but a geometric handoff, then the word death is the wrong word entirely. What we've been calling the heat death of the universe is, from the perspective of CCC, something closer to labor. The universe at maximum entropy, drifting in cold silence, is not dying. It is in the final stage of becoming something else, the vast emptiness, the infinite cold. The photons wandering through dark space for 1 Google years all of it is the gestation of the next Big Bang. We are living inside a universe that will eventually give birth, and the child will never know its parent existed. But this is only one cycle. Penrose says the sequence is infinite, and that infinity has a name. The mathematical machinery behind the conformal transition deserves more than a metaphor, though the metaphors help, so we'll use both. The technical tool Penrose employs is called conformal rescaling. In general relativity, the geometry of spacetime is described by a mathematical object called the metric. Essentially a rule that tells you how to measure distances and durations at every point in spacetime. Two spacetimes are conformally equivalent if one metric can be obtained from the other by multiplying it by a smooth function at every point. This function can vary across space and time. It can be enormous in some regions and tiny in others. What it cannot do is introduce new angles or change the causal structure. Which events can influence which other events? Which paths through spacetime are available to light? In plain terms, conformal rescaling changes the size of everything, uniformly and smoothly, without changing the shape of anything. It's the mathematical equivalent of zooming in on a photograph. Every distance changes. Every proportion stays identical. When Penrose applies conformal rescaling to the future boundary of a dying universe and the past boundary of a new one, something remarkable happens. The two surfaces, one representing the asymptotic infinity of a universe that has expanded forever, the other representing the explosive origin of a universe just beginning, become mathematically identical under the rescaling. They can be glued together, smoothly, without a seam, without a discontinuity. Without requiring any physical process to connect them, the mathematics simply recognizes them as the same surface, expressed at different scales that no longer mean anything. Two strips of fresh tape pressed together at room temperature don't need glue. Their surfaces are physically compatible. The intermolecular forces do the rest. The conformal boundaries of adjacent aeons are like that, compatible by nature, requiring no external mechanism to join them. The geometry does the work. But once the boundaries are identified, once the end of one aeon and the beginning of the next are recognized as the same geometric surface, a question immediately follows. What, if anything, crosses that boundary? What information, what structure, what physical reality passes from one universe to the next? The answer comes in three parts, and the third one is where things get genuinely strange. Matter does not cross. By the time a universe reaches its conformal boundary, all matter has been destroyed. Protons have decayed or been consumed by black holes. Black holes have evaporated through Hawking radiation across 1 Google years. The atoms that built every star and planet and living creature are simply gone. No atom survives the journey. No molecule carries its structure forward. Information, in the conventional quantum mechanical sense, also does not cross, at least not in a recoverable, decodable form. The specifics of which particles existed, which quantum states they occupied, the entire detailed history of a universe's contents, this does not transfer in any readable way. The next universe does not inherit a memory of the previous one, the way a child inherits memories from a parent. It inherits something more like bone structure, something deeper than memory, written in geometry rather than content. What does cross is the conformal geometry of spacetime itself, the causal structure, the shape of the light cones, the mathematical skeleton of how the old universe was organized, and layered on top of that skeleton, something more specific, the gravitational wave imprints of the most energetic events in the previous universe's history. Think about what happens when you delete a file on a computer. The file is gone from the directory. The operating system no longer knows it exists. But on the physical surface of the hard drive, the magnetic domains that encoded that file have not been scrubbed. They've only been marked as available for reuse. The data is gone for practical purposes. the physical trace remains. A sufficiently sensitive forensic tool can still detect that something was there. The new universe is a hard drive that has been reformatted, not magnetically wiped. The contents are gone. The traces are not. Those traces are gravitational. In the previous aeon, the most energetic events were the mergers of supermassive black holes, objects millions or billions of times the mass of the Sun, colliding over timescales that dwarf the current age of our universe, releasing energy in gravitational waves that dwarfs anything else the cosmos produces. These gravitational wave bursts, generated in the final eons of the previous universe, carry enormous energy. In the CCC framework, that energy does not simply dissipate at the conformal boundary. It imprints. It crosses into the new universe as a structured pattern, a set of concentrated energy signals that propagate through the early moments of the new Big Bang and leave detectable marks on the distribution of radiation. Marks that we might be able to see, not in some hypothetical future detector. In data we already have, in measurements we have already made, in a map of the sky that has been sitting in our archives for decades, examined by thousands of scientists, published in thousands of papers, a map that may contain the fossil signatures of events that happened before time began. That trail of evidence leads directly into one of the most dramatic and contested episodes in modern astronomy, the place where two universes may have left their fingerprints on each other. Cyclic universes are not a new idea, not even close. In Hindu cosmology, time moves in vast cycles called kalpas. One kalpa, a single day in the life of Brahma. The Creator lasts 4,320,000,000 years. After each kalpa, the universe dissolves and is reborn. The ancient Greeks had their own version, the Stoic concept of eternal recurrence, the idea that the cosmos periodically consumes itself in fire and reconstitutes from the ashes, repeating the same history in endless cycles. In Norse mythology, Ragnarok ends the world and the world rises again from the waters. Across cultures, across millennia, human beings have looked at the cosmos and intuited that it might be going around in circles. But intuition is not physics. Poetry is not mathematics. Every ancient cyclic cosmology shared the same fundamental limitation. It was a story, not a calculation. Nobody could tell you the mechanism. Nobody could write down the equations. Nobody could make a prediction you could test with an instrument. That's the difference with CCC. It is not mythology dressed in scientific language. It is a specific mathematical framework, constructed within the established geometry of general relativity that makes falsifiable predictions. The cycles it describes are not metaphors. They are geometric transitions with calculable properties and observable consequences. But before we get to the observations, let's be clear about what kind of cycle Penrose is actually proposing, because it is not what most people imagine when they hear cyclic universe. The most familiar version of a cyclic cosmology is the big bounce the universe expands, reaches maximum size, reverses, collapses, back to a singularity in a big crunch, and then explodes again in a new Big Bang. This is an intuitive picture, almost satisfying in its symmetry. Expansion, contraction, explosion, repeat. The universe breathing in and out. It's also wrong. Or at least, it doesn't describe the universe we live in. In 1998, two independent research teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, published observations of distant Type 1a supernovae, showing that the universe's expansion is not slowing down. It is speeding up. The discovery earned the Nobel Prize in Physics in 2011. The expansion of the universe is accelerating, driven by what we call dark energy, and there is no known mechanism that would reverse it. The universe will not collapse. It will expand forever, growing emptier and colder, until it reaches exactly the heat-death state we've been describing. CCC accepts this completely. Penrose is not fighting the data. He is following it all the way to the end and then asking what the end actually means. In CCC, the sequence goes like this. Aeon 1 begins with a Big Bang. The universe expands, structure forms, stars ignite, galaxies assemble. Civilizations possibly arise and possibly ask questions about the nature of reality. Then the stars die. Matter decays. Black holes evaporate. The universe reaches its conformally invariant endpoint, massless, timeless, scaleless, and that endpoint is geometrically identified with the Big Bang of Aeon 2. Aeon 2 unfolds, evolves, ends, and becomes the origin of Aeon 3, and so on, without limit in either direction. No first Aeon, no final Aeon, no edge to the sequence. This resolves several problems simultaneously, and it's worth naming them clearly. The question, what came before the Big Bang, has haunted cosmology since the moment the Big Bang was confirmed. Every answer either invokes a prior state that requires its own explanation, or retreats into the laws of physics break down at the singularity, so the question is meaningless. Neither answer is satisfying. CCC dissolves the question from a different angle entirely. If there is no first Aeon, there is no before the first Big Bang to explain. The question assumes a starting point that doesn't exist, like asking what is north of the North Pole. The geometry simply doesn't have that edge. The low entropy initial condition, the improbability so extreme that Penrose calculated it at 1 in 10 to the power of 10 to the power of 123, also resolves naturally. Each new Aeon inherits a conformally clean starting geometry from the previous Aeon's endpoint. The low entropy is not a miraculous coincidence. It is a structural feature of the conformal transition, delivered automatically by the mathematics, requiring no fine-tuning and no external agency. And unlike the string theory landscape, which resolves the fine-tuning problem by proposing an unimaginably vast number of parallel universes with different physical constants, most of which can never be observed or tested. CCC requires only one universe at a time. Sequential, not parallel. Testable in principle, because each Aeon leaves physical traces on the next. Now consider the position of our own universe within this infinite sequence. In CCC, our current Aeon is one link in a chain that extends infinitely in both directions. How far along the chain are we? The honest answer is that there is no way to know. The number of Aeons that preceded ours could be 10 to the power of 10 to the power of 100, a number whose digits, if written in proton-sized font, would require a space vastly larger than our observable universe just to contain. Our Aeon might be the 10,000th, or it might be a number so large that no notation in any mathematics we've ever developed could represent it. We are, in the most literal sense, somewhere in the middle of a story that has no beginning and no end. You might be thinking if that's true, if we're one anonymous Aeon in an infinite sequence with no memory of what came before, then what's the point? What does it mean? The question feels destabilizing, like finding out your entire life story is one sentence in a book that fills a library the size of a galaxy. But that's the wrong frame. The right question is, does an infinite sequence diminish the significance of each individual Aeon, or does it confirm it? If every Aeon runs the full arc from Big Bang to heat death, if every Aeon contains the full drama of cosmic evolution, the ignition and death of hundreds of billions of stars, the possibility of life and thought and inquiry, then every Aeon is complete in itself, not a fragment, not a draft, the whole story told once more, with whatever variations the conformal geometry allows, including ours, every galaxy we can see, every star whose light reaches us, every moment of human history complete, whole, not a rehearsal for something later, not a repetition of something earlier, its own thing. The universe is essentially Netflix, no series finale, every season a new Big Bang, and nobody remembers the previous seasons unless, of course, something left a mark. And this is where the story gets genuinely unhinged, because Penrose claims he actually found those marks. The mathematical elegance of CCC, the way it dissolves the entropy problem, the way it sidesteps the question of what came before the beginning, the way it produces smooth and flat initial conditions as a natural consequence of the conformal transition. All of this is intellectually beautiful. Beauty in physics is worth something. History has repeatedly shown that mathematically elegant theories tend to be pointing at something real, but beauty is not evidence. For CCC to be science rather than sophisticated philosophy, it needs to make contact with physical reality. And the most direct form of contact, the most concrete requirement embedded in the theory structure, involves one of the most fundamental particles in the known universe. The proton has to die. Not immediately, not soon, not in any time frame that feels threatening to daily life, but eventually, according to CCC, every proton in the universe must decay. Every proton in every atom of every planet, of every star system, in every galaxy must, given enough time, cease to exist as a proton and dissolve into lighter particles. If protons are truly stable forever, if they genuinely never decay under any circumstances, then the universe cannot reach the fully massless, conformally invariant final state that CCC requires. Some mass would always remain. The conformal boundary would never be clean. The transition to the next ion would be disrupted. So do protons decay? In the framework of grand unified theories, the family of models that attempt to unify three of the four fundamental forces into a single theoretical structure, proton decay is predicted. The proton is not fundamental. It is made of quarks, and under GUT models, there exist processes through which those quarks can interact via new hypothetical particles, called X-bosons, and rearrange into lighter decay products. The predicted half-life for proton decay through the most commonly studied channel, a proton decaying into a positron and a neutral pion, is greater than 10 to the 34th years. That's 10,000 trillion years. This is, to put it mildly, difficult to test directly. You cannot watch a single proton for 10 to the 34th years and wait for it to pop. But you can watch an enormous number of protons simultaneously and look for the rare statistical event when one of them decays during your observation window. If the half-life is 10 to the 34th years, then in a sample of 10 to the 34th protons, you'd expect roughly one decay per year. A detector containing 50,000 tons of ultra-pure water holds approximately 1.7 times 10 to the 34th protons. Watch it carefully enough, and the math says you should occasionally see one go. This is exactly what the Super Kamiokande detector in Japan was built to do. Among other things, located 1 kilometer underground in a zinc mine in Hida, the detector is a cylindrical tank holding 50,000 tons of ultra-pure water, lined with over 11,000 photomultiplier tubes, sensitive enough to detect the faint flash of light produced when a charged particle moves through water faster than light travels through that medium. Super Kamiokande has been running since 1996, watching those protons, waiting. As of 2024, it has seen nothing. Not one confirmed proton decay event. The null result has allowed physicists to set what's called a lower bound on the proton's half-life. For the specific decay channel most favored by GUT predictions, proton decaying into a positron and a neutral pion, Super Kamiokande has established that the half-life must be greater than 1.6 times 10 to the 34th years. The experiment has essentially looked at the problem and said if protons decay through this channel, they do so more slowly than our most optimistic models predicted. Does this break CCC? No, and it's important to understand precisely why not. CCEC does not require proton decay to happen at any particular rate. It requires only that proton decay eventually happens on timescales that could be 10 to the 40th years, 10 to the 50th years, or far beyond. The Super Kamiokande result rules out certain fast decay channels predicted by specific GUT models. It does not rule out proton decay in general, and it does not conflict with CCEC in any direct way. The theory operates on timescales so vast that even the most conservative experimental bounds on proton stability are comfortable orders of magnitude short of what CCC needs. Think about what we're actually doing when we run Super Kamiokande. We have built a chamber of extraordinary cleanliness and sensitivity, filled it with 50,000 tons of water, buried it a kilometer underground to shield it from cosmic rays, staffed it with physicists who have dedicated careers to watching water in the dark, and we are waiting collectively, generationally, for a particle that may not decay for 10 to the 34th years or longer. And we call this science, which it absolutely is. It is science operating at the boundary of what human patience and engineering can accomplish. There is something almost philosophical about the endeavor. We are sitting in a tank of water, in a mountain, in the dark, staring at protons and willing them to break. We cannot even be certain our civilization will exist long enough to see a result. We might be watching the wrong decay channel. The proton might be stable through every process we've predicted and decay through some mechanism we haven't thought of yet. That is exactly what great science looks like. Not certainty, commitment. The proton's stubbornness doesn't close the door on CCC, but it does mean that the most accessible test of the theory is not the proton. It's something else entirely. Something already archived, already analyzed, already hanging in every representation of the observable universe we have ever produced. And you don't need to wait 10 to the 34th years to look for it. The evidence may already be hiding in data we've collected from the night sky. 380,000 years after the Big Bang, the universe did something it had never done before. It became transparent. For the first 380,000 years of cosmic history, the universe was a dense, opaque plasma, a seething fog of electrons, protons, and radiation so tightly coupled that light could not travel more than a short distance before being absorbed and re-emitted. Photons were prisoners, perpetually scattered, perpetually redirected, unable to carry information anywhere. The universe was lit from within, but invisible from without, like a room so thick with smoke that you can see the glow, but not the walls. Then the temperature dropped to roughly 3,000 Kelvin. At that point, electrons slowed enough to be captured by protons, forming neutral hydrogen atoms for the first time. The fog cleared. The universe became transparent almost simultaneously across its entire volume, and the photons that had been trapped in that plasma were suddenly free. They streamed outward in every direction, carrying with them a perfect thermal imprint of the state of the universe at that precise moment. Those photons are still traveling today. They have been traveling for 13.8 billion years. They have been stretched by the expansion of the universe from visible light wavelengths down to microwave wavelengths, cooled from 3,000 Kelvin to 2.725 Kelvin, just barely above absolute zero. They arrive at our detectors from every direction in the sky, uniform, to a precision that is almost disturbing. The temperature variation across the entire celestial sphere is only about 1 part in 100,000 fluctuations of roughly 30 millionths of a Kelvin against a background of 2.725 Kelvin. This is the cosmic microwave background, the CMB, the oldest light in the universe, a snapshot of the cosmos at 380,000 years old. preserved across 13.8 billion years of travel. Arriving at our instruments right now as you read this, every CMB photon that lands on a detector anywhere on Earth today has been in flight since before the Milky Way existed, before the Sun existed, before the Earth existed, before the first generation of stars had finished burning. It is, without exaggeration, the most ancient signal we will ever be able to detect, a photograph of the universe in its infancy, taken automatically, developed by physics, delivered across the entirety of cosmic time. Penrose looked at this photograph and asked, what if it contains a message from before the photograph was taken? In the framework of CEC-ECC, the conformal boundary between the previous aeon and our own is not a clean erasure. It is a surface through which the geometric imprints of extreme energy events can propagate. And the most extreme energy events in the final stages of any aeon are the mergers of supermassive black holes. To calibrate what extreme means here, a supernova, the explosive death of a massive star, releasing more energy in a few seconds than the sun will emit across its entire 10 billion year lifetime, is among the most energetic events we can directly observe. A merger of two supermassive black holes, each containing the mass of billions of suns, releases energy in gravitational radiation that dwarfs a supernova by factors that require scientific notation to express. These are the loudest events the universe produces. In the final long eons of a dying aeon, as the last supermassive black holes slowly evaporate through Hawking radiation. Occasional mergers between them represent the last great energetic outbursts before silence. According to CCC, the gravitational wave energy released by those mergers does not simply dissipate at the conformal boundary. It crosses. It impresses itself on the geometry of the new aeon's early moments, and that impression eventually manifests as a subtle thermal anomaly in the CMB, a small, roughly circular region where the temperature is slightly elevated above the surrounding background. Not dramatically elevated, subtly. The signal would be small enough that standard CMB analyses, not looking for it, would easily overlook it, but it would be there. Penrose named these predicted anomalies Hawking points, in honor of Stephen Hawking, a recognition that the signals originate from the final evaporation events of black holes in the previous aeon, the very process Hawking's 1974 radiation theory describes. In 2010, Penrose and his collaborator, Vahe Gurzadian, published an analysis of CMB data from NASA's WMAP satellite, the Wilkinson Microwave Anisotropy Probe, and reported finding approximately 12 circular anomalies in the data consistent with what CCC predicts. The circles were small, spanning roughly 0.1 to 0.2 degrees across the sky. Their temperature was slightly elevated relative to the surrounding CMB. Their statistical distribution appeared, by Penrose and Gurzadian's analysis, to be non-random. Then came the Planck satellite, the European Space Agency's definitive CMB observatory, launched in 2009, providing maps of the CMB with angular resolution approximately 3 times sharper than WMAP and dramatically improved sensitivity. The most detailed portrait of the cosmic microwave background ever produced. Between 2018 and 2020, Penrose, along with Daniel Ann and others, published analyses of Planck data claiming to identify 6 particularly prominent Hawking points compact, slightly warm circular features whose statistical properties, under their analysis, were inconsistent with random noise. 6 points, tiny circles of warmth, spanning less than 1/4 of a degree on the sky, each one potentially the echo of a supermassive black hole merger from a universe that died before our time began. Somewhere in the sky above you right now, in the microwave glow that bathes the Earth from every direction, there may be a message, faint, ancient, written in the only language that survives the death of a universe, the geometry of light. The previous aeon could not send matter. It could not send atoms or photons or any conventional signal. But it could leave a gravitational indent on the fabric of space-time itself. And that indent could propagate through the conformal boundary and express itself as warmth a few millionths of a degree warmer than the space around it. Look up at the night sky. Somewhere in that darkness, in the invisible microwave frequencies our eyes can't detect, there may be the echo of a black hole that evaporated before our Big Bang, a remnant of an event so ancient that the word ancient loses all meaning, a whisper from a universe that had no idea another universe was listening. Penrose is essentially saying this: the previous universe left us a message, and after 13.8 billion years, we finally built instruments sensitive enough to read it. The argument about whether we're reading it correctly, well, that's where things get complicated. And that's exactly what's happening, because not everyone agrees those signatures are real. Science is not a collection of facts. It is a process for stress testing claims until they either break or hold. The process began almost immediately after Penrose and Gurzadyan published their 2010 WMAP analysis. Within months, 3 independent research groups had obtained the same publicly available WMAP dataset, run their own statistical analyses, and reached conclusions that contradicted the original paper. The group of Moss, Scott, and Zeben published their reanalysis and found no statistically significant evidence for the concentric circular anomalies that Penrose and Gurzadyan had reported. The team of Wehuus and Eriksson performed a separate examination and similarly concluded that the circles claimed in the original paper were not distinguishable from what you would expect in a standard cosmological model with no CCC signal. A third analysis by Hadjian reached the same conclusion through yet another independent method. 3 groups, 3 independent approaches, 1 consistent result. The evidence does not hold up. The central objection raised by all 3 teams cuts to something fundamental about statistics and human cognition. The problem is known in different contexts as the look elsewhere effect, or p-hacking, or in its most familiar everyday form, the simple fact that if you search hard enough for a pattern in random data, you will find one. The human brain is, at its core, a pattern recognition machine. This was useful when our ancestors needed to distinguish a tiger from shadows in tall grass. Erring on the side of seeing patterns that aren't there is cheaper than missing patterns that are. But that same bias becomes a liability in data analysis. If you define your search criteria loosely enough, or examine enough different statistical measures, or look at enough features in a large data set, the laws of probability guarantee that something will appear unusual. The question is never whether unusual things exist in the data. They always do. The question is whether they are more unusual than what random fluctuations produce by chance. The CMB is an extraordinarily rich data set. It contains temperature measurements across the entire sky at millions of resolution elements. In a data set that large, circles, arcs, clusters, and anomalies of countless varieties will occur by pure chance. The statistical question is not, are there anomalies, but are there more anomalies or more significant anomalies than a universe without CCC signals would produce? According to the 3 reanalysis groups, the answer in 2010 was no. Think of it this way. Take a photograph of a static-filled television screen. Stare at it long enough, and your brain will find faces, landscapes, animals' patterns assembled from pure noise by a nervous system that evolved to find patterns. The patterns are not in the photograph. They are in the act of looking. This is not a flaw in human perception. It's a feature that kept our ancestors alive. But it is a profound liability in scientific analysis. And it is precisely why independent replication and pre-registration of hypotheses exist as scientific norms. Penrose and his collaborators did not accept the reanalysis results quietly. Their response was substantive. The critiquing groups, they argued, were not searching for the right kind of signal. The statistical tests applied by Moss, Scott, Zibin, Wehus, Erickson, and Hajian were designed for a different type of CMB anomaly and were not optimized to detect the specific signature that CCC predicts. Looking for a CCC signal with the wrong statistical tool, Penrose's team argued, is like searching for a faint radio signal with a telescope designed for visible light. You might genuinely find nothing and be genuinely wrong about its absence. This methodological dispute about which statistical test is appropriate, about what the signal should look like before you know whether it's there, about how to define significance when your hypothesis was formed after initial examination of the data has not been resolved. It remains live. It is the kind of scientific argument that requires more data, better methods, and time. More data arrived in the form of the Planck satellite results. ESA's Planck Observatory operated from 2009 to 2013, producing CMB maps of unprecedented precision, roughly 3 times the angular resolution of WMAP, with substantially reduced instrument noise. If the Hawking points claimed in the WMAP analysis were real physical signals rather than statistical artifacts, they should appear with greater clarity in Planck data. In 2020, Penrose, Daniel An, and their collaborators published an analysis of the Planck dataset claiming to identify 6 prominent Hawking points features that their statistical analysis characterized as highly anomalous relative to simulated CMB maps generated without CCC effects. The community is still evaluating this claim. The threshold for a credible cosmological discovery is demanding. In particle physics, the standard for announcing a new particle requires what's called high sigma significance, meaning the probability that the observed signal arose from random fluctuation is less than 1 in 3,500,000. The Higgs boson, announced in 2012, cleared this bar. The Hawking points reported by Penrose's team sit at roughly 2 to 3 sigma, statistically interesting, genuinely worth investigating, but not yet at a level where the physics community would accept them as confirmed detections. A 2 sigma result has roughly a 1 in 20 chance of being a statistical fluctuation. A 3 sigma result drops that to roughly 1 in 370. Neither is 0, and neither is discovery. This is not a scandal. This is science working correctly. Every legitimate discovery in the history of physics passed through a period of disputed evidence before the data accumulated sufficiently to force consensus. Continental drift was called nonsense for 4 decades before ocean floor spreading confirmed it. Gravitational waves were theorized in 1916 and not directly detected until 2015. 99 years of absence of evidence before LIGO heard 2 black holes collide. The history of science is not a clean progression from ignorance to knowledge. It is a contentious, iterative, frequently frustrating process of claim and counterclaim, reanalysis and rebuttal until reality finally becomes undeniable. The skeptics are right to be skeptical. The 2 to 3 sigma result genuinely might be noise. The methodological objections are legitimate and unresolved. There is no dishonesty on either side, only the ordinary difficulty of extracting a faint signal from a complex and finite data set using tools whose appropriateness is itself under debate. But if the skeptics are wrong, if those 6 warm circles in the Planck data are what Penrose says they are, then we are holding in our hands something that has no precedent in human history. Evidence of events that occurred before our universe existed. Physical traces of a cosmos that lived its entire arc, billions of years of stars, possibly civilizations, definitely black holes, and died, and passed something of itself through the boundary into us. That would be worth the argument. And that argument leads to the deepest dispute of all, not just about the physics, but about the nature of what it means for a human mind to know anything at all. CCC is a minority position in cosmology. That's a fact, and it's worth stating plainly before anything else. Not a fringe theory, not pseudoscience, not the work of someone who has lost the thread of rigorous thinking. Roger Penrose is one of the most decorated mathematical physicists alive, a Nobel laureate, a fellow of the Royal Society, the man who proved that singularities are an unavoidable consequence of general relativity, the co-developer of the Penrose-Hawking singularity theorems that form a cornerstone of modern cosmology. When he proposes something, the physics community listens carefully, even when it disagrees. CCC is a minority position, not because it is irrational, but because it lacks the decisive observational confirmation that would compel the majority to revise their priors. That's a very different thing. The history of science is littered with minority positions that turned out to be correct, and the pattern is uncomfortable enough that it should give skeptics pause. Alfred Wegener proposed continental drift in 1912. His evidence was striking. The coastlines of South America and Africa fit together like puzzle pieces. The fossil records on opposite sides of the Atlantic matched species that could never have swum across it. The geological strata on separated continents showed identical formations. The scientific establishment spent 40 years dismissing him, sometimes with open contempt. The mechanism he proposed was wrong. He suggested continents plowed through the ocean floor like ships through water, which is physically implausible. But the core claim was right. When ocean floor spreading was confirmed in the 1960s through paleomagnetic data, plate tectonics became the foundational framework of geology overnight. Wegener died in 1930 on a research expedition to Greenland, vindicated by no one. 20 years before the data arrived, Ignaz Semmelweis, a Hungarian physician working in Vienna in the 1840s, noticed that puerperal fever, a deadly infection killing mothers after childbirth, was dramatically more common in wards staffed by medical students who came directly from performing autopsies than in wards staffed by midwives. He concluded that something on the doctor's hands was causing the deaths, and he instituted mandatory hand washing with chlorinated lime solution. Mortality in his ward dropped from roughly 10% to under 2%. The medical establishment rejected him, ridiculed him, and eventually had him committed to a mental institution, where he died at 47. Germ theory, developed by Pasteur and Lister in the following decades, proved he was right. He was not rewarded. He was destroyed for being correct too early. Science progresses by being wrong, then less wrong. The mechanism is not elegant. It is not fair. It involves careers staked on ideas that may not be validated within a single human lifetime, and it involves the people holding those ideas absorbing professional costs for the privilege of being right before their time. Against that backdrop, examine what CCC requires physically, the conditions that must be true for the theory to work, and assess them honestly. First, proton decay. As established in Part 10, the non-observation of proton decay through 2024 does not rule out CCC. It constrains the rate. The half-life of the proton must be greater than 1.6 times 10 to the 34th years through the most studied decay channel, and CCC is comfortable operating on timescales far beyond that. Second, the neutrino problem. This one is harder. Neutrinos, the ghostly, near-massless particles produced in nuclear reactions, passing through the Earth in their trillions every second, have been confirmed experimentally to have mass. The evidence came from neutrino oscillation experiments, where neutrinos were observed changing between their three flavors, electron, muon, and tau during flight, a process that can only occur if different mass states exist. The Nobel Prize in Physics in 2015 was awarded to Takaaki Kajita and Arthur MacDonald for this discovery. CCC, as initially formulated, requires all massive particles to eventually disappear. A universe containing even very small but non-zero neutrino masses presents a problem. Those masses need to go somewhere. Penrose acknowledges this directly. He does not wave it away. His response is that the resolution likely requires physics. We have not yet discovered some mechanism through which mass itself becomes dynamically unstable at extreme timescales and temperatures, dissolving through processes that don't exist in the standard model as currently formulated. He is careful to label this for what it is: speculation, not a calculated prediction, a placeholder for future theory. The gap is real, and he owns it. Third, electrons. The electron is extraordinarily stable. No experiment has ever detected electron decay, and theoretical lower bounds on its lifetime exceed 10 to the 26th years. For CCC to work, electrons too must ultimately vanish. The mechanism is unknown. Some extensions of the standard model permit electron decay under exotic conditions, but nothing confirmed or even strongly predicted. Another placeholder, another gap. A theory that requires new physics to fill multiple structural gaps is, reasonably, treated with skepticism. It should be. That's the correct scientific posture. But the question worth sitting with is, does a theory requiring undiscovered physics indicate that the theory is wrong? Or does it indicate that our current physics is incomplete? Because our current physics is definitely incomplete. We know this with certainty. The standard model has no satisfactory account of dark matter, which constitutes roughly 27% of the universe's energy content. It has no account of dark energy, which constitutes roughly 68%. It cannot reconcile quantum mechanics with general relativity. Two theories that individually pass every experimental test we can devise, but are mathematically incompatible with each other at the Planck scale. The standard model is not the final word. It is the best current approximation. Every theory that reaches beyond it will require, by definition, physics that doesn't exist in the current model. Demanding that CCEC operate within the standard model is demanding that a theory about the universe's ultimate fate respect the known limitations of a framework we already know is incomplete. That standard, applied consistently, would have prevented general relativity from being taken seriously in 1915, because it reached beyond Newtonian mechanics in ways that felt unmotivated at the time. Penrose is 93 years old, born in 1931. He has been doing serious mathematics for over 70 years. He is, by any measure, still actively producing research, still engaging with critics, still refining CCC in response to objections, still giving lectures and writing papers, and defending a position he believes the mathematics compels him toward. He is, in a very real sense, placing a bet that cannot be settled in his lifetime that he will be right about what happens 1 Google years from now. In a regime of physics, no experiment we can build will directly access. He has no expectation of personal vindication. He is doing it anyway. If that is not intellectual courage, the phrase has no meaning. But whether CCC is right or wrong, it has done what every great theory must do. It has changed the questions we're capable of asking. What came before the Big Bang? That question has never been comfortable. For most of human history, it was a theological problem dressed in cosmological language, the moment before the moment of creation, the question that pointed at God or at nothing, both answers equally vertiginous. When cosmology confirmed in the 20th century that the universe genuinely had a beginning in time, the question became scientific without becoming answerable. Every cosmological model that attempted to describe a before ran into the same wall. The equations of general relativity break down at the Big Bang singularity. Time itself ceases to be defined in any standard sense, and the notion of before becomes operationally meaningless within the framework that is supposed to answer it. CCC dissolves this question not by answering it, but by exposing it as malformed. There is no before the Big Bang in CCCCC because there is no first Big Bang. The sequence of aeons extends infinitely in both temporal directions. Asking what preceded the first aeon is like asking what lies south of the South Pole. It is a grammatically correct sentence in English. It is not a meaningful question in geometry. The South Pole is not the bottom edge of the Earth. It is a point on a surface that has no edges. Travel south from anywhere on Earth, and you will eventually pass through the South Pole and continue northward. The directionality inverts smoothly, continuously, without a wall or a void or a special event marking the transition. CCC does the same thing with time. There is no edge to the temporal structure of CCC's universe. There is no outside. There is no moment that is the first moment. No aeon that is the initial aeon. No Big Bang that had nothing before it. The structure is closed under the conformal equivalence that connects each aeon's end to the next aeon's beginning. You can ask, what happened in the previous aeon, and get an answer within the framework. You cannot ask, what happened before all aeons? Because the framework has no such location. This does not mean the question is stupid. It means the question was built on an assumption that time is a line with a left end that CCC replaces with a different geometry. Questions built on false assumptions don't get answered, they get dissolved. And dissolving a question that has haunted 2,000 years of philosophy and theology is not a minor thing. Now turn from the question of beginnings to the question of what we are within this structure. The standard cosmological picture, without CCC, places humanity in a particular kind of story. We exist in the one universe that has ever been. We are the temporary products of a process that began in an explosion and will end in cold silence. And the entirety of what can ever exist or think or matter is confined to the narrow sliver of cosmic time between the Big Bang and the heat death. That's a story with weight. It is not obviously comforting. There is a school of thought associated with thinkers like Bertrand Russell and Steven Weinberg that looks at this picture and finds it clarifying. The universe is indifferent. It will end. Meaning is what we make of it in the interim. CCC does not offer easy comfort either, but it places us differently. We are not the last act of a one-time performance. We are one chapter in a book with no first page and no last page, infinite in both directions. Every chapter complete in itself. The universe of our aeon is not a survivor clinging to the last stages of a dying story. It is a full expression. With 13.8 billion years already behind it, and more than one Google years still ahead, of a pattern that has instantiated itself an inconceivable number of times and will continue to do so without limit. That doesn't make us large, but it makes us part of something whose scale places large and small out of useful range. Consider the light. Every CMB photon captured by a telescope today has traveled for 13.8 billion years to reach the detector. It left its source the surface of last scattering, the moment the universe became transparent before any star in the Milky Way existed. If CCC is correct, some of those photons carry within their distribution the geometric imprint of supermassive black hole mergers from the previous aeon. They are not merely ancient, they are trans-aeon. They have crossed the boundary between cosmic epochs, survived the conformal transition, propagated through our aeon's entire history, and arrived now. Receiving a photon like that would be like finding a letter with no return address, written in a script no living language can decipher, from a civilization that ceased to exist before the concept of civilization existed. The sender is gone completely, irreversibly gone, dissolved into the conformal geometry of the transition. No atom of that previous universe survives in our aeon, no structure, no memory in any conventional sense. Only the faint indent left in the geometry of space-time by the last great violence of that universe's dying, a gravitational whisper, a thermal echo, a circle of warmth, barely distinguishable from the surrounding noise. 13.8 billion years of cosmic history represents approximately 10 to the negative 88th of the full duration of a single aeon. Written as a fraction, 1 divided by 10 to the 88th power, we are at the very beginning. The stars of the Milky Way are young. The universe we can observe has barely started spending its low entropy inheritance. The full arc of this aeon, the era of stars, the era of white dwarfs, the era of black holes, the slow evaporative quiet of the final eons stretches ahead of us for a duration that makes our entire history so far look like the first syllable of the first word of the first sentence of an infinitely long book. If human civilization persists not for centuries, not for millennia, but for billions and trillions of years, evolving into forms we cannot predict or imagine, what might be learned from the signals of the previous aeon? What questions could be asked that we cannot even formulate yet? Using instruments built on physics we haven't discovered, reading a map that has been traveling toward us since before our Big Bang, and on the other side of that question, what will our aeon leave behind? When our universe's last supermassive black holes finally merge and evaporate, 1 Google years from now, the gravitational wave bursts from those events will cross the conformal boundary into the next aeon. They will imprint on that aeon's CMB as Hawking points, something of the geometry of our universe, not its contents, not its history in any readable form, but the shape of its most extreme events will persist. We'll be there, on the other side, not as memory, as geometry, as the faint structural consequence of the fact that we existed. And that question not about the past, but about the future and what we owe to it is where science meets something deeper than science. We started this journey with a death sentence. The universe would end in heat, death, cold, silent, absolute. Every star extinguished, every atom decayed, every black hole evaporated across 1 Google years until nothing remained but photons drifting through infinite dark. Most cosmologists looked at that picture and called it the final chapter, a complete story. Closed. Penrose looked at the same picture and saw something different. Not an ending, a redefinition of what ending means. This distinction matters more than it might initially appear. Penrose does not dispute heat death. He does not claim the stars won't die, that black holes won't evaporate, that entropy won't reach its maximum. Every piece of the standard picture remains intact. What he disputes is the interpretation, the assumption that maximum entropy, no massive particles remaining, conformally invariant final state equals terminus. His argument is that this state is not a wall, it is a door. Not because something miraculous intervenes, but because the mathematics of conformal geometry, applied rigorously within the framework of general relativity, reveals that the door was always there. We just weren't looking at the right part of the wall. That reframing from ending to transition, from terminus to boundary, is the conceptual revolution at the heart of CCCC, and it rests on 3 pillars that are worth naming cleanly before we assess where the theory stands. The first pillar is mathematical. Conformal invariance, the property shared by the universe's final massless state and its earliest near-massless state, permits the conformal rescaling that identifies the 2 boundaries. This is not hand-waving. It is differential geometry, applied within the same mathematical framework that describes black holes, gravitational waves, and the expansion of the universe. The math does not require new postulates. It requires following existing postulates to a conclusion that most people stopped short of reaching. The second pillar is physical, the low entropy initial condition of the Big Bang. The one that Penrose calculated to be improbable at 1 in 10 to the power of 10 to the power of 123 emerges naturally from the conformal structure of the transition between aeons. No fine-tuning required. No appeal to an unspecified mechanism that arranged things just right at the start. The geometry of the conformal boundary guarantees a low entropy beginning for the next aeon automatically, as a structural consequence rather than a miraculous coincidence. This solves, in a single elegant move, what has been the most uncomfortable unsolved problem in foundational cosmology for decades. The third pillar is observational potential, contested, but real. The Hawking points small circular regions of slightly elevated temperature in the cosmic microwave background, predicted by CCC as the imprint of supermassive black hole mergers from the previous aeon, reported by Penrose and collaborators in analyses of both WMAP and Planck satellite data. 6 prominent candidates identified in Planck data as of 2020, currently sitting at 2 to 3 sigma statistical significance, not confirmed, not dismissed, in the arena, being tested, being argued over, waiting for better data and better methods to render a verdict. Now place CCC alongside its competitors and the contrast sharpens. The string landscape combined with eternal inflation proposes that our universe is one bubble among an effectively infinite number of bubble universes, each with different physical constants, nucleating continuously in an eternally inflating background space-time. It explains fine-tuning through the anthropic principle. We observe the constants we do because only certain combinations permit observers to exist. It is mathematically sophisticated and theoretically rich. It is also, in its current form, essentially impossible to test directly. No observation we can make from within our universe can confirm or deny the existence of other bubbles. A theory that cannot in principle be falsified occupies an uncomfortable position in the philosophy of science, regardless of its internal elegance. Loop quantum cosmology offers the big bounce quantum gravitational effects prevent the singularity. The collapsing universe reaches a maximum density and rebounds into expansion. It preserves some information across the bounce and avoids the infinite density problem of classical singularity theories. The difficulty is the 1998 supernova data. The universe's expansion is accelerating. Dark energy is driving the cosmos apart at an increasing rate. There is no known mechanism that would reverse this acceleration and produce a collapse. Loop quantum cosmology requires a universe that eventually stops expanding and turns around. Ours shows no sign of doing that. CCC requires no reversal. It requires no parallel universes. It operates in one universe at a time, sequentially, leaving observable predictions and data we can actually collect. The Hawking points are small and faint and statistically contested, but they are there, in the sky, in data sets we already possess, subject to analysis by anyone with access to the Planck satellite archives. You can test this, not easily, not decisively yet, but in principle, with better instruments and better statistics. The question has an answer that the universe is capable of providing. This is what Karl Popper called falsifiability, and it is the property that separates science from everything else. A claim that makes no predictions that could in principle be wrong cannot be scientifically confirmed either. CCC makes a specific quantitative prediction about the distribution of temperature anomalies in the CMB. That prediction is either right or wrong. The universe knows which. We are building the tools to find out. Whether those tools will return a verdict that vindicates Penrose or refutes him, no one can say. The data will decide. That is the only honest answer available. But step back from the verdict for a moment. Step back from the sigma levels and the methodological disputes and the unresolved neutrino mass problem and the waiting for proton decay that may never come in any human time frame. Step all the way back to the simplest possible version of what has happened in this story. A human being. One person. Sitting at a desk with a pencil and a pad of paper and a mind trained over decades in the language of geometry, looked at ancient light that had been traveling for 13.8 billion years. Applied mathematical tools developed over a century by dozens of brilliant predecessors, and concluded that this light might carry the echo of a universe that died before our universe began. And then he looked further and saw that our universe's death 1 Google years from now, in cold and silence, and the last evaporation of the last black hole would itself send an echo into whatever comes next. That the geometry of our existence would persist in the only form geometry allows, as a faint imprint on the CMB of an aeon that will never know we were here. One person, one planet, 13.8 billion years of cosmic history distilled into a calculation that reaches 1 Google years in both directions. When our universe finally reaches its conformal boundary after 1 Google years of expansion, after the last supermassive black hole releases its final pulse of Hawking radiation and dissolves the gravitational wave, imprints of that dissolution will cross into the next aeon, somewhere in the CMB of a universe that won't exist for longer than we can express. There will be a Hawking point, a circle of warmth, a few millionths of a degree above background. The geometric consequence of the fact that our universe existed, that it contained mass and structure, and the merging of enormous black holes, that it ran its full arc. No name, no record, no content, just the shape, the faint structural indent, the proof of presence without the presence itself. When that last photon crosses the conformal boundary into the next aeon, when the final signal of our universe's dying propagates forward into a cosmos that will never know what produced it, will it carry any trace of the fact that once, briefly, in the early morning of this aeon, on a small planet around an ordinary star, matter organized itself into nervous systems that looked up and asked, "Oh, why?" We started with a simple question: what happens after the universe ends? The answer led somewhere language barely reaches. It may be that there is no after. It may be that ending and beginning are the same word, written in 2 different dialects of mathematics, and that what we call the death of a universe is, from the perspective of conformal geometry, indistinguishable from a birth. C might be correct, it might not. The science is unresolved. The evidence is contested. The unconfirmed physical requirements are real obstacles and not minor inconveniences. The verdict is genuinely open. But the larger truth, the one that sits beneath the sigma levels and the methodological disputes, is that not knowing is not a failure. It is the natural condition of a species that exists for roughly 1 part in 10 to the 88th of a single aeon and attempts to comprehend the whole of infinite time. We are not failing to understand the universe. We are succeeding, slowly and imperfectly, and with enormous effort, at understanding more of it than any previous generation could. The incompleteness is not embarrassing. It is the accurate description of where we stand. Every CMB photon passing through space right now, through the walls of every building, through the atmosphere, through the instruments we have built to catch them, might be a messenger from a dead universe, or it might simply be the echo of our own Big Bang, ancient and remarkable enough on its own terms. We don't yet know which. What we know is that we are asking that a species that appeared on this planet a few 100,000 years ago, in the early seconds of the cosmic morning, has already built instruments sensitive enough to detect temperature variations of 30 millionths of a Kelvin across the entire sky, and is using them to look for fingerprints left by a universe that may have died before our time began. The final answer may live in a telescope not yet designed, in an algorithm not yet written, in a mind currently looking up at a night sky somewhere. watching the stars without knowing yet what questions to ask, but already feeling the pull of the dark between them. The universe owes us no explanation. It did not arrange itself for our comprehension. It has no obligation to be legible. But every time we ask anyway, every time we stand at the boundary of what is known and lean forward rather than back, we are doing the most extraordinary thing matter has ever done anywhere in the observable universe. We are thinking about ourselves